Okay. What I want to do today is I want to give you another distribution. Looking at the homeworks, I'm kind of okay with where you're at. I do have to address one thing about what a z-score is and what it isn't. And why do you people keep thinking the percentages are z-scores? Right, Aaron? Okay, so what I've given you is students' t distribution. Students' t, here's what it looks like. This chart is very similar to what we've done in the past, but it's reversed. So with the normal distribution, the field of the table was your area amount. Right, the area under the curve in the field of the table. With students t, now that we understand the concept of hypothesis testing and setting an alpha, we're just going to look for the values of t that meet our alpha. Right? So it just reverses what we've done in the past. Right? But it's still sort of the same concept. So what we have here, if we look at this table, the very first row, if we have 1 degree of freedom, and we're looking for whether or not our t-score is 0.025 in the tails, which is our 95% confidence interval, we need a t-score that is equal to or greater than 12.706. So again, the field of the chart is the actual t-score that you're looking for. Given what you've decided in your decision rule should be your alpha, should be your cut point, should be your this is significant, this is not significant, I can reject the null hypothesis or I can't. All right, and we're going to walk through an example today. But this is very similar to what we've already done. It just so happens that the math is identical to the z-table and creating a z-score with little small differences. All right. Let me explain to you why we have to have a different distribution. Because if you're looking at this, what kind of shape is this? It looks like a bell curve, right? Well, there's a slight difference. This is the normal curve with a t distribution overlaid on top of it. And if I find the smallest possible sample size, so that's a sample size that we have only 2 observations in our data set. This blue line is actually the shape of the t distribution. So compare the blue line to the yellow line and tell me, how does it look different? What's higher? The peak is higher. Okay. So what does that mean? Because remember, we're talking about the area under the curve. And if the peak is higher, what does that mean for, let's say, the tails? What?
Less area in the tails.
In which distribution?
In the yellow.
Which is the normal distribution. Okay? So the normal distribution are yellow. Most of the area is where? In the middle. And we know this already because we remember our empirical rule, which says that 68% of our observations are within 1 standard deviation from the mean. Okay? With students t, this distribution, when you look at the tails, we're taller in the tails, right? In this area right over here. We're taller in the tails. And the overall height of the curve is shorter because that area has been displaced out to the tails. It's as if you sort of squeeze down on the top, but the area can't get out. It can't escape. And so what happens when you squeeze on a balloon from the top? It gets wider. Okay. So this t-distribution looks a lot like our bell curve. It is still symmetrical. It still is centered on the idea of the mean, and we still give it a value of 0. But the only thing that's different is that there's more of the area in the curve. The reason for this is the t-distribution was built to deal with small samples, like you guys as a class. I had a student in my office. She's a senior. She has to do a survey for her capstone paper in psychology, and she asked if she could come survey you guys. And I said, well, you could, but I only got like 20 on my best day. And you really want a larger sample. This student's t-distribution is designed for when you have a small sample like you guys. Now, as we increase the sample size, I just clicked on 25. I increased the sample size to have an n of 26, and therefore I have 25 degrees of freedom. Now what do we have? It's a lot closer. Is it perfect? No, it's not quite perfect. Because where are we looking for where it's not perfect? 2 spots. The height and the tails. These tails are still a little bit taller, and the peak of the curve is a little bit shorter than a normal distribution. Let's go up to 30. Again, n of 30, or 30 degrees of freedom. We're still closer, but you still see the little bit of tiny gaps. 35, 40, 45, up to 50. We're pretty close at 50, right? You can still see a little bit of the blue, but for the most part, it's the same. So as our n increases, the student's t-distribution becomes more like a normal distribution. And at a certain point, they actually converge. They actually are identically overlapping. How many degrees of freedom for students t to normal? This is one of those things where I never really wanted to know what the exact number is. It won't say, because Google's not going to be that kind to me, because I just thought, hey, why don't you just Google it? Oh well, I'll look it up for next time. But it's somewhere between like 30 to 50 when you can go from one chart to the other. Okay. The chart that I gave you stops at like 38, and then after that it just says infinity. Right. There is a, you could list the degrees of freedom for every single number, but at some point it's going to just be the same. And when you look at the differences between the degrees of freedom of 36 and 38, the scores really aren't all that different. So if we go back and we look at our PDF copy here, right? So the difference between achieving this t-value of 1.306, 07, 09, 04, right? We're into the thousandths before you really see a difference. At some point, those numbers are just going to be all the same. Okay. So we have a new distribution. It's very, very similar to the normal distribution. And when we use it, we're just going to have a couple of small changes in how we use it and how we calculate statistics for it. So first of all, we're dealing with a sample, right? This is a small sample. So we're going to use S instead of sigma, because we no longer have the population variance. We no longer have that population spread. What we have now is the spread of our sample. So we're going to use a small s. This distribution actually has a neat sort of history behind it. Students is a pseudonym. Like with the Federalist Papers, how you have Publius writing the Federalist Papers. The person that actually invented this distribution is W.S. Gossett, and he worked for Guinness. And what Guinness wanted to know was they had lots of ingredients coming in, making their beer, and you want to do quality control. So what they wanted to figure out was, using the least amount of waste as possible, how could they sample their raw ingredients? I think this is specific to barley in the paper that was written, right? To test whether or not the barley is good or not, so you don't make spoiled beer. But Guinness wanted to protect its reputation, so it didn't allow its workers to publish under their names. So imagine if Coastal, didn't allow me to publish under my name, because they didn't want the world to know what Coastal was up to. Guinness didn't want you to think that they were trying to do quality testing of their product on only 3 grains of barley. Because if you test the 3 grains of barley, that's 3 less grains of barley you have to make beer. Makes sense, right? So it was published under this pseudonym of Students T, and Student as the author. And it's based upon the idea of degrees of freedom. And I've mentioned these before. When you calculate a test statistic, you sort of use up one of the observations. And the remaining observations are your degrees of freedom. The concept of degrees of freedom comes from the idea that if you wanted to sort of verify the statistic that you created, you could use the remaining ones to make sure that your calculations were correct. It delves into sampling theory and probability, and it gets really weird, so don't worry about it. But just understand that there's this idea out there known as a degree of freedom. And it's just simply n minus 1. Now that's going to be important to us because, again, we are going to be dealing with data sets that have small numbers of observations. And the shape of the t-distribution does actually vary between one degree of freedom to the next. The goal of statistics is to be as precise as possible, and when you have a distribution that gets fatter at the tails, where you're, again, trying to make those decision rule claims about rejecting the null hypothesis, you got to pay really good attention to when you're around those cut points. So degree of freedom. You guys can subtract a number from another number, correct? Especially just one. Okay, you can do that. You just count backwards and you're there. So that's not hard. I've already kind of shown you this idea that the distribution, as your number gets smaller, it gets wider. We used to be able, with the normal distribution, to say, oh wait, I just remember a magic z-score, and that was 1.96, because 1.96 gave you 5% in the two tails. Well, you can't really do that anymore, because that number of t changes for the number of degrees of freedom. So you couldn't just say, oh, I'm going to memorize t equals 2.201, because that only applies to an n of 12, which gives you 11 degrees of freedom. You're not going to memorize that. The other reason I put this up here is because I wanted to show you how by adding more area into the tails, it pushes that decision rule out a little bit. So you have to go further out into the distribution. It's still the same area. So the area here equals the area like here. It doesn't look right, but you have to trust me. That's what it's built upon. Okay. It's the same things. The only thing that I've done to these equations is take the z out and replaced it with the t. So look at the first one. That's the same. We just have the n minus 1 at the bottom. Right? So finding s, finding the variance of your sample is the same. The sum of the difference from the mean squared divided by n minus 1. Again, this is a sample variance. You've done this before. This is the exact same equation. There's no t or z that's in that. You've done this before. You'll grumble over anything. You're like, ah, math with letters. Grumble, grumble, grumble. It's not that bad. The second thing we need to know is our standard error. And we introduced that a couple of weeks ago when we were talking about difference of proportions or difference of means test. Right? The standard error of your statistic. Well, that's just the variance of s divided by the square root n. Again, nothing difficult here. Yes, for the square root sign, you got to turn your phone sideways. Now here is where we first encounter t. There's students t. Look at that equation. You guys can do that equation in your sleep. As long as you have the right numbers, right, Joey? Because all you're doing is subtracting your sample mean from what you think the population mean is and dividing that by the standard error. That's all it is. It's the same exact thing you do for z-scores. Same exact thing. Now, a couple of other steps might be a little different. Right? The first two things, I kind of just usually give you that sigma at the bottom, but I've taken the sigma out, which you're not paying enough attention to anyways. and you have to calculate that. But you're going to be paying attention to your sample size anyways, because you have to calculate your degrees of freedom. Now, if we want to reverse engineer this, and we want to solve for the values of x, to get our confidence intervals, that's what it looks like when you remove things and move them around. Okay. So let's think about this for a second. All we have is a situation where you have a smaller sample, so you're not going to assume that the sample is the same normally distributed as it was before. You're going to say, oh my gosh, my n is 25. I can't just use a standard normal distribution anymore. I can't calculate z-scores. I have to calculate a t-score. Why? Because with an n of 25, how many degrees of freedom do you have? You have 24 degrees of freedom. 24 degrees of freedom, oh, it's on the t-chart. I must have to use this. Now, if you had 65 degrees of freedom, do you have to use the t-chart? No. Could you? Yeah, you just use that little infinity line at the bottom. And look, it says 1.96. That's your normal distribution. Okay, so you really only have 3 steps. 1 is find your S. 2, find your standard error. And then 3, either find the confidence interval or find your t-score. Whatever it is that you're trying to do for the question. That's all you have to do. Okay. So again, you've all done the same things before, but now we're just sort of treating it in a different sense by saying, wait a minute, our sample's small. We can't assume away the shape of our distribution. We're going to take the shape of the distribution into account when we make our decision of whether or not the value that we get for t is over that threshold. So we're not going to automatically reject the null hypothesis if our t is above 1.96. We're going to have to look to see what the appropriate value of t to reject is. Okay. I chose a different way of looking at this for a very specific reason. All right? I want to make sure we really understand what it is we're doing here. Now we have a sample. Our n is 30. Our sample mean is 79. And our sample variance is 8. Now, we want to make sure that if we're describing the population mean, how should we think of the population mean? So it's sort of like that margin of error thing, right? We want to have whether it's 95 or 90% chance. We want to know where our sample is around a population mean, because we don't know that. We know what our sample is, but we don't know about the population yet. So let's start with what we do know. Okay. We know our sample size, which now we know what? If we know our sample size, what other number do we need to figure out from that? Okay, so how many degrees of freedom do we have? Okay, is 29 on our charts? Yes, it is. Okay. Now, what kind of confidence interval do we want to build? So, how sure of a guess do we want to have when we guess at what the population mean is?
5%.
Okay. So with a 5% chance of being wrong. Why 5%, Jake? Because everybody uses that for everything else, right? It's either 5% or 95%, right? So we're going to have a 5% chance of being wrong. So let's look at our table. Which column gives us that 5% chance of being wrong? No. No. Why 0.025, Tom?
Distributed each tail adds up to 5%.
Yep. So Tom says, well, you have 5%, but remember you have two tails. So you got to take that 5% and divide it into 2, which gives you the 0.025, which is the middle column on your table. Here's the thing that I don't like. And I searched for different forms of tables to show you guys, because this table construction, you can redesign these things a million different ways. And I went with this one because it had the little thing at the top with the graph, and it reminded you that the number you're given for t is the amount in the tail. I couldn't find one that split that in half. I did find one that had it like at the top it said one-tailed, two-tailed, right? But then I'm like, yeah, people are going to get confused because it says both 0.05 and 0.025, right? So this is what we're going to stick with. We're going to stick with this idea that you have to remember to split it in the tails. Now, if you didn't remember that, but you do remember, wait a minute, Dr. Wood says 1.96 is sort of the z-score. Which column has a z-score of 1.96 at the very bottom? Which one, Tom? The middle one. Okay, so that's our magic column. For most things, we're going to use that middle column. Why? Because everybody else uses that number. Unless you're doing a homework question and it tells you with which percentage to be sure. Whether it's 90% to be sure or 99% to be sure. If you always have a choice, pick that 95% and pick that middle column. Does that make sense? Okay. Now we know we're going to use the middle column. And what's our degrees of freedom?
29.
So I'm going to use 29 degrees of freedom, and I'm going to look here in this middle column. And this is going to be the t-score that's going to represent having the 95% in the middle. We all okay with that? That number is 2.045. 2.045. How we write t, there's a couple of different things that you can do for when you write your t. Sometimes people like to put the degrees of freedom. Other times people will do that, and they'll also put what their alpha is, so 0.05. You'll want to come up with what makes sense for you, because that t-score only applies to us in one situation. When your n is 30 and you have 29 degrees of freedom, and your decision rule is 5% in the tails, right? Or 0.025, whatever. You have to remember that. Every question t is going to change. As your n changes, your t-score will change. So if I scratched out 30 and wrote 35, I now have 34 degrees of freedom. Is 34 on my chart? Yep. And what's the number for 34 degrees of freedom in the middle column.
2.032.
2.032. That's different than what I wrote down, right? It's not all that much different, but it is different. Okay. What else do I need? Well, I have my X bar. My X bar is 79. And I have my T, 2.045. What's S of X? Or S of my sample mean? What is that again? I'll give you a hint. It starts with S. That's the standard error. Okay. How do I compute the standard error? Well, standard error is S over the square root of n. But what is S? Oh, geesh. Yeah, they gave it to me. Thank you. All right? I didn't have to do this thing. And when I say I didn't have to do this thing, how many times would I have to take x and minus x bar? 30. If I gave you a data set of 30 numbers and I didn't give you S, you would have to build it by a nice long sheet of paper and writing all the numbers down, and then you find the mean, which we know is 79, and then subtracting them, and then squaring that, and then adding up those 30 numbers. You guys don't want to do that, right? Why don't you want to do that? It's too much work. And it's so much work that you're very likely to make a stupid mistake. Like some of you that think 0 times 1 is 1. And then that throws everything off. Some people did that in one of the homeworks where you had to do the frequency table. Remember that? And everybody thought it was like 132 over something, and it was actually like 76 over something. Those things happen. Because, there's a lot of numbers, and there's so many of them, and it's so hard. Okay. So luckily for us, we've been given S. But we still have to, we've been given S, but we still know that our standard error of X is S, which is 8, over what? Square root of 30. Somebody turn their phone on and give me that number, please. Take the number 8 and divide it by the square root of 30. Everybody's waiting for somebody else to do it. Don't make me make Abby do it by hand. She will. She'll be quicker than you guys. Does anybody else get that? Trust but verify. You get what you got? Okay. So here we go. We now have our S, our standard error of our sample mean, which is 1.461. Somebody take that and multiply it by 2.045. What's wrong, Joey?
Where are we getting this from?
Where are we getting what from?
This equation.
I gave it to you.
This
I'll show you what it is in a minute.
Yeah, I was looking at the 3 equations that you gave us on the last PowerPoint, so I didn't see what this came from.
It's right there. It's number 3.
We're going in, it's on the model,
Oh,
like,
okay.
right there.
Yeah. There it is, too. What do we got? 2.988.
2.988. You want it to round to 1,000.
I'm fine. Okay. So this thing that we have here, this 2.988, is going to be the same on both sides, right? The only difference is on one side we're going to subtract it from the mean, and the other side we're going to add it to the mean. So let's do the easier one first. Let's add 79 plus 2.988 is 81.988. And now somebody do the subtraction. It should be 76.012. Okay. Let me explain to you what we've done. What we have done is found the value of x that we think the sample mean tells us our population mean is between. Now, with z-scores, we've been doing this from the other side. Because in the other side, we have the population mean, and then we're trying to predict where our sample mean should fall within. What we've done is we've done it backwards. We have the sample mean. It's a small sample, so we have to use students t. But what we want to do is say, we think, given this information, the population mean is between these two numbers. But we don't have the population mean, right? Because we got a small sample. Okay. That's not a normal curve. That's a t-curve. I'm sure you can tell by the way that I made it a little shorter and fatter at the tails. Right, you all see that, right? Of course, yeah. Of course you do. Okay. So what do we have? Well, what we've calculated is we've calculated where we think mu could be. Mu, the population mean, is somewhere between 76 and 82. How does this help us? Well, let's go back to the reason that Students T was created, quality control. And instead of it being Guinness, let's say we just had a storm. It is, actually, here's something that's more topical. Anybody here have a Samsung Galaxy 7? Oh, you. Okay, not the Note, not the one that catches on fire. Okay. So you're Samsung, and you've got a phone. I'm just going to use yours for illustration purposes. You've got a phone that theoretically catches on fire when you're charging it or just having it on, right? The Note 7 will burst into flames if it's on. Uh-oh. Nick's like, oh, my cousin. Yeah, that's why you can't reach your cousin anymore, because they don't want to have their phone in their pocket and have it catch on fire. You're Samsung. You come out with the Note 8. How many of them do you want to test before you ship them all out? Do you want to test every single one of them? See, she gets it. Abby, why don't you want to test every single phone before you send them out? it would take a long time. If you're Guinness and you're making beer, how much of the Guinness do you want to taste before you send it all out? Why do you want to taste as little as possible, Jake? Because then that's Guinness you can't sell. Okay? So that's why when you're a student and you're a guy working for Guinness, you don't want to waste as much of your raw ingredients or your finished products as possible, because that drives down profits. You're Samsung and you've got the Galaxy Note 8, and you've got a bunch of very upset 7 customers waiting for their phone. How many of them should you test? Well, as little as possible, so that you can be comfortable in how many of them will catch on fire when you give them to your customers. That's the framework with which we're working in this example. That last equation that I used to do this, you're like, where did that come from? All I did was reconfigure the normal one, and instead of solving for z, which you're used to doing, I solved for mu. And we're not using the z distribution anymore, we're using the t, so I just swapped that out. So what I've done today, in kind of a tricky form, is I've taught you 2 things. One, there's an alternative distribution when you have small numbers, which is the t distribution, and you use that when you have, well, usually less than 50. I'll do some more Googling and come up with the right number. All right, but when your n is small, you use student's t. And now what else have I taught you? The concept of confidence intervals. You have a decision rule and you want to know what those 2 bounds are. Your lower bound and your upper bound. And those are just the values in which the 95%, which is what we chose in this example, are in the middle.